So in chapter 4.3, we're going to talk about the features of the regression line in more detail. We're going to understand the importance of avoiding extrapolation. We're going to compute residual and state the least squares property. We're going to construct and interpret residual plots, and we're going to determine whether outliers are influential in our calculations of a particular regression line. And then we're going to compute and interpret the coefficient of determination, the R-square value. Our first objective is to understand the importance of avoiding extrapolation. Although extrapolation is done a lot, in other words, sometimes we extrapolate when we don't have all of the information. But making predictions for the value of an explanatory variable that are outside the range of the data, which is called extrapolation, is not always very practical to do. And in fact, since we don't have all of the information of x and y, making those predictions may not be reliable. In the case of the house size versus the sale price, we notice that the values that were given to us were between these two values here. These we call the domain values of x. And so that our line is very well predicted within those range because those are the values that have been provided to us. Similarly, we were given the y values of the prices associated with those x, which are called the range values. So any ideas about a line that could actually happen beyond the domain of our x values is really invalid because that's what we call extrapolation. So we're going to compute the residuals and state the least squares property. So given a point xy on a scatter plot and the least square regression line y hat is equal to b0 plus b1 times x, the residual for the point xy is the difference between the observed value y and the predicted or expected value y hat. So it is this distance here which is considered our residual. For the least square regression line, for predicting the selling price from the house, size equals y hat equals 160.2 plus 0.0992x, we may compute a residual for the point 2555 and 426. The predicted value for y hat is 413. So the residual is the actual value of y given y hat. So the residual is 12.4. That's the distance from the point to the line. The idea of the least square property is the magnitude of the residual is just the vertical distance from the point to the least square line. The least squares line is the line for which the sum of the squared vertical distances is as small as possible. So in other words, the square of the residuals are as small as possible. It follows that if we square each residual and add up the squares, the sum is the least for the least squares regression line than for any other line. This is known as the least squares property, and that is considered the best fit line. So in some cases, we want to construct and interpret the residual plots to see if in fact we have obtained the right function to fit our data set. A residual plot is a plot in which the residuals are plotted against the explanatory variable x. When two variables have a linear relationship, the residual plot will not exhibit any noticeable pattern. If the residual plot does exhibit a pattern, such as a curve pattern, then the variables do not have a linear relationship, and the least square regression line should not be used. In some cases, we've always been trying to rely on the correlation coefficients to determine whether two variables have a linear relationship. When the correlation is close to 1 or minus 1, the relationship may not be linear. To determine whether the variables have a linear relationship, we construct a scatter plot and usually a residual plot as well. Notice that even in lines that look kind of linear, where we fit a line in, may have a correlation of close to 1, but the pattern is curved. And in those cases, we will see it on a scatter plot as well as on the residual plot as well. So we've done a residual plot for our data for x, which is the size of the square feet that we have. These were the y values. These were the costs, the price of the houses that were involved. This is y hat right here. This was y observed. And so when we take y minus y hat, we get the residuals here. So the residuals are in this particular column, and we plot them against the x values. And we don't see any particular pattern noticeable in this particular residual plot. So really, in some sense, the best fit line does work for this particular data set. There are a number of ways to create residual plots. We will show you how to do a residual plot on Excel, but for the TI-83 or 84, actually for the 83 there is a slightly different process. But the following steps are used typically to do a residual plot. So step one is you, of course, have the data in L1 and L2. You run the linreg command so that you can find the formula for the equation. Then if you plot if you set up the equation in, if you're using a TI-83, you can set up the equation in L3 so that you can find the predicted values for x. And we will show you that in class. And then you can find the residuals in L4 by subtracting the L2 from the L3. But if you don't have a TI-84, then you'll if you don't have if you have the TI-84, then you can use step 2. You can press the second equal, then 1 to access the plot 1 menu. You select on and the scatter plot and enter the residuals for the Y list field by pressing the second stats key, and then you can hit RESID. If you don't have that feature, we would have to show you how to use the plots key using the L1 and L4 capability. Then you press either graph or zoom 9 to view the plot. Notice if you use the graph feature, you'll have to use the windows to set up the scales. So for option TI-84, this is what you should get when you hit the second equal, and this is what the residual plot would look like. So our fourth objective is to determine whether outliers are influential points. An influential point is a point when included in a scatter plot strongly affects the position of the least square regression line. So in the following example, there are several lines here. One line includes Texas. So we consider the scatter plot of farmland versus total land area for the U.S. The blue line on the plot is the least square line computed for 48 states, not including Texas or Alaska, right? The red dotted line is the least square line for 49 states, including Texas. And including Texas moves that line somewhat. The green dashed line is the least square regression line for the 49 states, including Alaska. Including Alaska causes a big shift in position of the line. So you can see here's Alaska. This line has moved in that direction, including the line. Not including that point, or the Texas point, you get the blue line. So both points are somewhat influential. Influential points are troublesome because the least square regression line is supposed to summarize all the data rather than reflect the position of a single point. When a scatter plot contains outliers, the least square regression line should be computed both with and without each outlier to determine which outliers are influential. If there is an influential point, the least square regression line should be computed with both with and without the point, and the equation of both lines should be reported. This is to give the researcher or the person reading the study clues as to the effects of the outlier in the study. So now we want to compute the coefficient of determination, which is considered our R-squared value. So now we want to talk about explained and unexplained variation in our data set. So consider the least square line and the line y equals y bar. So here's our line y bar. For any point y xy, y minus y bar can be split into two parts. The first part is our predicted value, y hat minus y bar. The difference between the central value y bar, which is our mean value, and the predicted value y hat is called the explained difference. So the difference between this value and the line is called the explained difference and represents the difference explained by the least square line. The second part is called y minus y bar, which is, guess what? The residual. It is the difference between the observed values y and the predicted value y hat, which is just the residual. This difference is caused by factors unrelated to the least square regression line and is called the unexplained difference. This distance over here is the unexplained difference, the residual difference. The better the least square predictions are, the smaller the unexplained differences will be. We measure the size of the unexplained differences by squaring them and adding them together. This quantity is called the unexplained variation. The explained variation is found by a similar result with the explained differences. When two variables have a linear relationship, the correlation coefficient R tells us how strong the relationship is. The measure is often used to measure how well the least square regression line fits the data is R squared. The closer R squared is to 1, the closer the prediction is made by the least square regression lines are to the actual values on average. The quantity of R squared is called the coefficient of determination, and it can be shown by advanced methods that R squared is equal to the explained variation divided by the unexplained variation plus the explained variation. In other words, R squared is the explained variation over the total variation. Thus, the R squared measures the proportion of the total variation that is explained by the least square regression line. Sometimes we see the equation this way: total variation in the data is equal to the explained plus unexplained. So in our previous example, the correlation between the size and the selling price for the following data was computed to be R at 0.90 approximately. What is the coefficient of determination? How much variation in the selling price is explained by the least square regression line? To find the coefficient of determination, we just square the correlation coefficient. And when we square it, we get the answer 0.811. The coefficient determination is 0.811. Therefore, 81.1% of the variation in the selling price is explained by the least square regression line on X, the size of the house. The R-square value gives us some information on how well the data fits the regression line, period. So, in this chapter 4-3, you should know that to extrapolate outside the domain and ranges of the data should be avoided. You found out how to compute residuals, which is y minus y hat. You knew about the least squares property, which is the sum of the residuals are as small as possible. You found out how to construct the use of residual plots to determine whether or not it is appropriate to use the least square regression line, especially if it is in fact a linear line. You found out how influential points affect the least square regression lines and what to do in finding those influential points. And finally, you know how to compute and interpret the R-square value, which is the coefficient of determination. Well, that concludes Chapter 4, and you should look at some problems and be working on the next project.